Okay, you guys. So we're going to be talking about right triangle trig here. And you did learn this in math too, so it's a little bit of a refresher. Some old hippie caught another hippie tripping on acid. That's so katoa. It's how you can kind of remember how to solve right triangles, right? So it's like sine is one of them, cosine is a trig function, and so are tangent. Sine is equal to the opposite over the hypotenuse, cosine is equal to adjacent over the hypotenuse, and tangent is equal to the opposite over the adjacent. And usually it's referring to from an angle, and usually the angles are denoted by this little circle with a line through it that is called theta. It's a Greek letter. So if I'm looking at this is the theta, that is the opposite side, and this is the adjacent side, the one that's touching it. And then the hypotenuse is always across from the right angle. If this were the theta up here, opposite would be this side, and this would be the adjacent. So it depends on which angle that you're looking at. So we kind of solved right triangles using sine, cosine, and tangent, or SOHCAHTOA. The inverse trig functions are cosecant, secant, and cotangent. You're going to hear those in trig, and you're going to hear those as you move on through your math career. Cosecant is denoted, you know how sine, this is the full word, but we shorten it to sin, and cosine, we shorten it to cos, tangent, we shorten it to tan. Cosecant gets shortened to CSC, and it is the flip of the sine. Secant is the flip of the cosine, and cotangent is the flip of the tangent. I remember it because cotangent and tangent make sense, and then C and S's always go together. It would be better if, secant was the flip of the sine, and cosecant was the flip of the cosine, but it's not like that. We got to confuse you. So cosecant is the flip of the sine, secant is the flip of the cosine. What am I saying? Oh, let's see this example. If the cosine is 2/3, the secant would be 3/2. So if they're asking you, which no one really does, it's just something I thought I should make sure you know, that secant is a flip of the cosine, secant is a flip of the cosine, secant is a flip of the cosine, cosecant is a flip of the sine, cosecant is a flip of the sine, and cotangent is a flip of the tangent. All right? So those are the 6 trig functions you'll ever have to know. Sine, cosine, tangent, cosecant, secant, and cotangent. Those are the 6, as you learn later in trig. So if I'm like, find all 6 trig functions, which I used to, if we were in school, I would have made you do a quiz about this. But so sine, you have sine, cosine, and tangent, and then cosecant is a flip of the sine, secant is a flip of the cosine, and cotangent is a flip of the tangent. So once you get these 3, you just flip them. So if this is the given picture, you're going from the theta. Remember, we're doing SOHCAHTOA. So sine is the opposite over the hypotenuse, opposite over the hypotenuse, so 12/13. Cosine is adjacent over hypotenuse, so 5/13, and tangent is opposite over adjacent, so opposite over adjacent, so 12/5. And then once you have those 3, you can just write in the flips for the other 3. Yeah? And let's say we weren't given this 13, then we would just use the Pythagorean theorem, right? Which is what I did down here. So if you're not given one of the sides, you can find the side. Okay, so find all 6 from this picture. This picture, I hadn't given you the red. So a squared plus b squared equals c squared is the Pythagorean theorem. We have this side, and this guy's the hypotenuse. 5√2 is the hypotenuse because it's across from the right angle. So we have one side plus, we're looking for this side, equals the hypotenuse squared. So 5 squared goes to 25, b squared stays the same. 5√2 squared is really 5√2 times 5√2. When you have 2 numbers with a radical, you end up doing outside times outside, so 5 times 5, and then inside of the radical times inside of the radical, so you get √4. And the square root of 4 is really 2, so 25 times 2 makes 50. So that's how this 5√2 squared ends up actually going to 50. So we have 25 plus b squared equals 50. Subtract over the 25, b equals 5. So that's how we get that last side. Now when we have all 3 sides, we can look at our 6 trig functions. And if that's theta, we're looking at sine, opposite over hypotenuse, so 5/5√2, which I'm going to get to the simplification in a second. And then cosine, adjacent over hypotenuse, tangent, opposite over adjacent. So that's how I got these. For the time being, so these 5s can cancel and it can go to 1/√2. For the time being, we're going to leave this like this. But there's a key. In math, you can't have radicals in the denominator of a fraction, or what I call it, rats in the basement. You can't have a radical in the basement of the fraction. So We have to learn to rationalize the denominator. So rationalizing the denominator is getting those rats out of the basement. So you know how we had 1 over root 2? All you have to do to rationalize the denominator, it's like a no-no in math. It's like dividing by 0. You have to multiply by what the bottom is over itself, because root 2 over root 2 is really just algebraically 1. That's why it's algebraically sound that I can multiply it to that. 1 times root 2 is root 2. Root 2 times root 2 is really square root of 2 times square root of 2 is square root of 4, which is 2. All you have to remember is that you multiply by the thing that is written on the bottom over itself, and then know that the square root of something times the square root of something just goes to the something every time. Like, look, you have 2 over square root of 3. You don't want that. You can't have radicals in the basement. That's not algebraically sound. So you multiply by what's in the basement over itself. This just becomes 2 root 3. You can't combine them and make it root 6, because this is different than underneath the radical. And then root 3 times root 3 just goes to 3. So the answer is 2 root 3 over 3. One more. 2 over root 6. You multiply by root 6 over root 6. This becomes 2 root 6. Root 6 times root 6 just gets 6. These can cancel then. The 2, 6 can go to 1/3. Root 6 over 3 is your final answer. So this is a really important thing as we move into the unit circle, rationalizing this denominator. Okay, next big thing on today, special right triangles. I don't know if you remember these from Math 2, but sometimes it's called the 30, 60, 90 triangles, or the 45, 45, 90 triangles. And these are the side lengths. 2 is always the hypotenuse on this guy. Root 3 is always next to the 30. 1's adjacent to the 60. And then with the 45, 45, 90 triangles, it's 1, 1 square root of 2. They actually come from, this one comes from an equilateral triangle where 60, 60, 60. And then you split it in half and do Pythagorean theorem. This guy actually comes from a square, and it's cut in half. A perfect square with 90-degree angles. That's how they split to 45, just so you know. So if I wanted to know, sine of 45, the sine of 45, I can pick either of those because they're both 45. Sine is opposite over hypotenuse, so 1 over root 2. But I got to rationalize the denominator, so multiply by root 2 over root 2 becomes root 2 over 2. Honestly, you'll learn to just switch this. If it's 1 over root 2, it just changes to this, so you just memorize it. Cosine of 60, so we go to 60. Cosine, adjacent over hypotenuse, 1/2. Cosecant of 30, that's the flip of the sine. So sine of 30, opposite over hypotenuse, 1/2. Cosecant would be 2 over 1. Tangent of 45, you can use either one. Opposite over adjacent, 1. Secant of 60 would be the cosine flip. So we flip that guy. Cotangent of 60. Cotangent is the flip of the tangent. So it would be adjacent over opposite. 60, adjacent over opposite. It would be, I did over hypotenuse. Adjacent over opposite, 1 over root 3. And then rationalize the denominator. So you can use these special right triangles in trig, and they're going to be a huge part of our lesson tomorrow when we're doing the unit circle. We put these into the unit circle. Okay, the last part of the notes today, only got a minute and a half, is solving these triangles. So given the sides, look for the angles. Ooh, actually, I'm going to ignore that for a second. This is what I want you to look at, really key. If you're given an angle looking for a side, so you're given an angle and you're looking for a side, you look at it and you're like, okay, what's the relationship? This is technically the adjacent, this is the hypotenuse. So you do cosine, because adjacent hypotenuse, AH, cosine of the angle equals x over 24.1. If x is on the top, if this is the proportion, you end up multiplying both sides by what's on the bottom. So you type in your calculator, literally 24.1 cosine 62, or type it into Desmos. The other type, there's 2 types of trig ones you're going to work through, where x is on the top or when x is on the bottom. And when x is on the bottom, see, look here, we're looking for x. 7 is the opposite, x is the hypotenuse, so opposite over hypotenuse, sine, SOA, sine of 22 equals opposite over hypotenuse. When x is on the bottom, you end up switching these two, really. So when a number is on the bottom, you multiply both sides by it, bada bing, bada boom. But when x is on the bottom, you have to switch these. You're technically multiplying both sides by x and then dividing off sine of 22. But really, we just switched this. If you just do 7 divided by sine of 22, you get your answer. So this is what your homework is on quizzes, is solving these triangles. It's from Math 2. Hopefully, it's an easier review. The other thing you aren't tested on, which I just thought I'd tell you that if you're given sides and you're looking for an angle versus looking for a side, you're looking for an angle, you have to use the inverse functions. So see how this is theta, and we're looking for this one? We'd say, okay, opposite over adjacent is tangent. So you type in literally tangent inverse of 413. It's a button on your calculator. Same with this one, like you have adjacent over hypotenuse, that'd be cosine, so cosine inverse of 4/5. It's literally a button on your calculator, but it's not a super important concept. Just thought I'd hit it. Solving right triangles is, though. This is important. Shoot me an email if this part isn't making sense. Okay, you guys rock.